What's up, guys? Today we're talking a little bit about span and linear independence. So last time, if you recall, we started talking a little bit about how you can take chunks of a vector space that have the same properties, that is, subspaces, and put them together to make other subspaces. Sometimes we could do this in a way that didn't contain extraneous information. This was when we had a direct sum. So we're going to try to kind of extend this idea. That is, if we have little chunks of a vector space, we're going to kind of ask ourselves, how little can we make those chunks? And using those littlest possible chunks, we're going to ask ourselves, how can we rebuild the whole space? That is basically the idea. It'll let us know, essentially, how a vector space is built out of smaller vector spaces. This will give us a lot of insight into the structure of vector spaces and help us to recover a lot of the classical tools you are used to using for dealing with vector spaces. So first off, we're going to define a linear combination. A linear combination of a list of vectors, which is an ordered sequence of vectors. So you've got a first vector, a second, and so on, all the way up to an mth vector, just elements of a vector space V. A linear combination of a list of these guys is just a sum of scaled vectors. So you take scalars, elements of your field, the underlying field, and then you multiply each one of the elements of your list all the way on down, and then you add it together. This is a linear combination. All right, cool. Pretty straightforward. So the idea is that we can use this to build subspaces. We'll talk about some of the intuition a little bit more first, but let's just present it straight away and prove a fact about it to get used to things. So, linear combinations, you take a list, which is an ordered set of vectors. It's not just like an unordered collection of vectors. It is vectors with specific order assigned to it. And what we can do with these guys when we add them and scale them together is we can build something which we'll call the span of those vectors. So the set of all linear combinations of a list of vectors is called the span of those vectors, the span of that list. And we'll denote this by the span of V1 through Vm. In other words, it is just the set of linear combinations, set of these guys right here, and that just ranges over field elements. All right, cool. So by convention, we're going to take the empty list to have span just the zero vector. This will make things a little bit easier because then we can say stuff like, the span of any list of vectors is a subspace or something like that, which in fact we will prove momentarily. But if we didn't take this convention, then we'd have to add a lot of additional little caveats. We'd have to say the span of a non-empty list of vectors is a subspace or something like that. So we'll just append this convention right here. The span of the empty list is just the set 0. This is just a convention, and it'll just make statements of theorems a little bit easier. There's nothing deep going on there. So let's prove our first theorem, and then we'll go back to talking about what's going on a little bit more. Here's the first theorem. Span is the smallest containing subspace. So if you take the span of a list of vectors, it is the smallest subspace containing all of those vectors in the list. Let's prove it. Okay. So first things first, let's notice some stuff. If V1 through Vm is a list of vectors in a vector space V, then 0v1 plus 0v2 and so on, all the way up to 0vm is 0. So 0, the 0 vector, is in the span of v1 through vm. That is a comma right there. Okay, so we've got the 0 vector in the span. Nice. Fair enough. Moreover, if a v1, or I'll even write it like this, if v is in the span of v1 through, pen's bugging out on me right there, vm, these are little v's, which I'm using little extra serifs right there, then v is equal to a1 v1 plus dot 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 all the way up to am vm for some a1 through am in the field, and for any, I'll say b in the field, we have that b v is equal to, well, b times a1 v1 plus all the way up to am vm, which is just equal to, and I'll write this just running across since it's only one more line right there, b a1 v1 plus dot 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 all the way up to bam, is a big A and a subscript m, vm, which, notice, it's a bunch of elements of the field times things in our list. It is in the span. It is of that form. So it is in the span of those vectors. Nice. Similarly, I will say if v prime, which I'll say is equal to a1 prime v1 plus dot 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 all the way up to am prime vm, is in the span of v1 through vm, then we can show that v plus v prime is just equal to, well, we've got a1 v1 plus dot 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 all the way up to am vm plus a1 prime v1 plus dot 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 all the way up to am prime vm. Okay, and just combining, we will get back, using associativity and commutativity, we will get back a1. I'm skipping kind of a step right there. I'm going to reorganize everything. So I put the v1s next to the v1s, and then I'm going to use, well, really what I'm going to use is distributivity, I guess. So I'll write out the step, a1 v1 plus dot dot dot, or actually let me write it out explicitly, a1 prime v1 plus dot 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 dot. So I've just kind of regrouped everything a little bit. am vm plus am prime vm. I'm just regrouping things into each, putting stuff that has a v1 next to stuff that has a v1 and so on. Okay, cool. And now using distributivity, I can take this to be a1 plus a1 prime v1 plus dot 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 all the way on down to am plus am prime vm. Okay, and hey, this is in the span of v1 through vm. That is, it's a bunch of elements of our field times the vectors in our list. Nice. So, by a theorem we proved last time, the span of v1 through vm is a subspace of v. That is, it's got the zero vector, it is closed under scaling, and it is closed under addition. So it is a subspace. Nice. All right. So it's a subspace. Cool. It is a subspace. We've got that down. We need to show that it's the smallest subspace and that it contains all the vectors in the list. Okay. Moreover, notice that I will write this way. Vi is equal to, I will write it as 0 v1 plus dot 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 0 vi minus 1 plus 1 times vi plus 0 times vi plus 1 plus dot 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 up to 0 times vm. So vi is in the span of v1 through vm, which I am maybe being slightly lax right here because I guess vi could be v1, so in that case you'd put a 1 right here and zeros next to everything else. But basically what I'm trying to say is, hey, if you take a linear combination with all of the scalars 0 except for the one you want to keep, you put a 1 right there, you recover that vector. Pretty nice, right? Ah, cool. Okay, fair enough. So you have each one in there. Okay, so it contains the whole list. Nice. Easy enough. Now, suppose W is a subspace of V, and V1 all the way up through Vm, all these guys are elements of W. Then, since linear combos of V1 all the way up through Vm are certainly also contained in W, span of V1 all the way up through Vm is contained in W as well. Hence, that span is the smallest subspace, and we are done. Kind of cool, right? Let's sort of zoom out a little bit and think about this real quick. That I wrote out in its full tedious glory, but basically all we had to do is say, hey, look, let's show that the span of a list of vectors is a subspace, that it contains all the vectors in the list. Okay, cool. That is done by right here. So this is showing that the span of terrible V1 all the way up through Vm is a subspace containing all those guys. This little last part, it is the smallest one. That is, if you pick any other subspace, then that subspace, if it contains all of these guys, all of the elements on our list, then it certainly contains the span of those elements, since a subspace has to be closed under addition and scalar multiplication, and linear combinations are just additions of scalar multiplications of the elements of the list. All right, cool. So you can see that there is some kind of nice parallel going on here. Before, we were taking subspaces of a vector space and finding out a way to put them together to make another subspace. Here, we're taking elements of a vector space and we're finding out how to put them together to make a subspace. So we see that there is a connection between subspaces of a vector space and other subspaces, and we see there's a connection between elements of a vector space and the subspaces of a vector space. Let's explore this a little bit further by proving some more results. Okay, so we're going to prove a lot more results about span and the subspaces we can build from lists of vectors, but it's going to be a lot easier if we have a few things to use to talk about what's going on here. That is a couple of additional terms so we don't have to say such long statements. So the first off is spans. So instead of saying that span of the list V1 through Vm is equal to V or some subspace or something like that, what we're going to instead say is that that list spans V. So if the span of some list is equal to a vector space, where those elements are vectors in that vector space, we'll say that that list spans the vector space. Whole lot easier than writing span of all this stuff equals v. Instead, we'll just say this thing spans v. All right, cool. So a very straightforward thing we could look at is we could say, hey, when is a vector space spanned by a finite list? That is, sometimes maybe you can't find a list of vectors that is only finitely long that spans a vector space, but other times you certainly can. So we'll say that a vector space is finite dimensional. Notice we haven't really defined dimension yet. This is just a term we're saying. We don't have a notion of dimension so far. We will build up to one. But for now, we'll say that a vector space is finite dimensional, implicitly noting that we don't really have an idea of what dimension means yet. This is just kind of a stand-in term. We'll say that it's finite dimensional if there is some list of vectors in it that spans the space. So a list, a finitely long ordered collection of vectors such that the span, that is the set of all linear combinations of those finitely many vectors, is equal to the whole space. Okay, cool. Naturally, if something is not finite dimensional, we'll call it infinite dimensional. All right, cool. So remember, by definition, every list is going to have finite length. A list is going to be, I mean, you could say something else. You could say, like, if there is some finite list of vectors, and you could, remove this requirement. But just to make things a little bit easier, let's specify that every list has finite length. Okay, cool. So finite length, if there's not a spanning list of vectors, we're going to call a vector space infinite dimensional. All right, here, let's do some examples. So here's a bit of notation and a definition. If you take a function from a field to a field, we'll call it polynomial with coefficients in f if there are elements of the field a0 up through am such that the function can be written in this form. That is, the output p of z for any z is equal to a polynomial in z. Okay, cool. We all know about polynomials. There is one piece here that maybe I should stress. There's a slight caveat here. So there is a difference between polynomials and polynomial functions if we are working in finite fields. That is, if our field is finite, there are, all functions in a finite field from a finite field to itself are polynomial, but there are multiple different polynomials that correspond to the same function. So there is a slight difference in that case, but in practice, if we're dealing with the reals or the complexes, which we mostly will be, we don't have to worry about this. So let's just assume that we are for now. All right, cool. So if we take script p of f to be the set of all polynomials with coefficients in f, here meaning all polynomial functions specifically, then for m a non-negative integer, we could also define Pm of f to be the set of all polynomials with coefficients in f and degree at most m. Here, degree is the highest power of m that pops up in an expression writing p as a polynomial of this form. Okay, cool. This is the place where it matters, the distinction between polynomials and polynomial functions for finite fields, because there can be polynomials with different degree that define the same polynomial function on a finite field. But like I said, let's just ignore that for the moment. If you want to learn more about that, I can send you some good resources. And yeah, it is kind of a fun little interesting fact. But if it seems at all confusing, just ignore it and go, hey, we're only talking about the reals and the complexes or something like that, and everything will be fine. So here are some good examples. So here, let me see if I write this over here. Well, here, let me think. Do I want to do this quite yet? Yeah, why not? Okay, so the polynomials of degree at most m. Let's take a quick example here. Notice that the polynomial functions of degree at most m with coefficients in a field f. This is a subspace of the polynomial functions of arbitrary degree on f, i.e. add together two polys of degree m, get back degree, I should say at most m, get back a poly of degree at most m. Similarly, scale a polynomial of degree at most m, get back a poly of the same degree. Or, if the scalar is 0, a lower degree polynomial. Okay, so it's definitely closed under scaling, definitely closed under addition. We can write out this fact just by writing two polynomials in this form with different coefficients, put some primes on the a's and so on, add them together, group things up, and you can see it right away. But I'm assuming that everyone has added together polynomials before in lots of algebra classes and is fairly familiar with how degree works. So naturally, I think that this statement is hopefully not too surprising. Similarly, it's pretty clear that if you have a polynomial of degree at most m for m a non-negative integer, then certainly Pm of f, the polynomials of degree at most m, definitely contains the 0 polynomial. All right, cool. Easy enough. So notice I should make that like scripty. Pm of f is equal to the span of the polynomial functions, which I'll write in the following way. 1, the constant polynomial function, the polynomial function z, the polynomial function z squared, all the way up to z to the m, where I'm being maybe a little bit loose right here. If m is equal to 0, then this would be only the span of the constant polynomial. If it's equal to 1, then it would just be 1 and z. If it's equal to 2, it would be 1z and z squared. You get exactly what I mean. What I'm trying to say is that it's the list of the monomials that are powers of z, up to z to the m. This is pretty straightforward, I think, because if you look at what a polynomial of degree m looks like, it looks like a linear combination of monomials, powers of z. So that is just what a polynomial of degree m is. It is an element of the span of these guys. So Pm of f is finite dimensional. However, P of f is not. And once again, this is a place where I should be clear. If you are working with finite fields, you have to be a little bit careful. If f is a finite field, then you have to be a little bit careful to distinguish between polynomials and polynomial functions, since this statement may not be true in this case. If you are just considering polynomials over the finite field, then this is still true. If you are considering polynomial functions, you have to be much more careful because there are polynomial functions, different ones that, or there are different polynomials that correspond to the same polynomial function, so this may not actually be the case. In fact, it is not the case. But that is something that we don't need to focus on at this moment. So basically, just imagine the reals or the complex numbers. The fact that the polynomials over a field like that are not finite dimensional makes some sense. After all, if it were the case that they were finite dimensional, then there would be a list finitely long of polynomials such that every polynomial could be represented as a linear combination of them. Take the polynomial of highest degree in that list, and that would say that every polynomial is of degree at most that number. But you can make polynomials of arbitrarily high degree, so certainly that is not the case. So the polynomial functions for f a big enough field, right, not a finite field, is not a finite dimensional vector space because it's not spanned by a finite list. Huh, cool. All right, so now that we've got a couple of terms that we can use to talk about things, let's get into proving results. Okay, so our first result is going to be about linear independence and dependence. Once again, a couple more definitions, and then we'll actually get to it. So a list of vectors, we're still talking about lists of vectors in a vector space V, we'll say it's linearly independent if the only choice of field elements that makes a linear combination of the vectors in that list equal the zero vector, that is the additive identity of the vector space, is the choice where you take all of those scalars, those field elements, to be the zero of the field, that is the additive identity of the field. We'll also, by convention, declare the empty list to be linearly independent, once again, just to avoid some awkward statements of theorems. So, naturally, if we've got a notion of linear independence, we will have a notion of linear dependence. That's when something is not linearly independent. So we'll say that a list of vectors is linearly dependent if it's not linearly independent. That is, a list of vectors is linearly dependent if there are field elements, not all zero, such that you can add together those vectors scaled by those field elements and get zero. Okay, so basically what we're getting at is something sort of similar to what we were talking about with direct sums and the nice fact that we only ever had to check whether or not there was one and only one way to write the zero vector to see if a sum was direct. So this is basically the exact same thing. The motivation here is essentially the same. That is, if there is more than one way to write the zero vector, then there's going to be more than one way to write every vector in the span, since every vector can be written as something plus the zero vector. All right, fair enough. So this is basically capturing whether or not the span of a list of vectors contains extraneous information, extra information. That is, did we actually need all of the vectors in the list to get the span, to get that subspace? Or could we just have taken a chunk of that list and gotten the same thing using span? So the linear dependence lemma captures this, and this will be a very important tool for us. This extremely, very much so, relies on the fact that we are looking at lists of vectors. That is, it's not just an abstract set of vectors, it is an ordered collection of vectors. So I'll explain what I mean. The linear dependence lemma says that if you have a linearly dependent list, then there is some k such that vk is in the span of v1 through vk minus 1. That is, there is some element where that element is in the span of all previous vectors in the list. This is where the order part pops up. If you are just talking about a set of vectors, then you don't have an order, and it is not clear what this would mean. We are explicitly using the order right here. Okay, cool. And we get some nice consequences of this. If k satisfies the condition above, that is, if vk is in the span of v1 through vk minus 1, and the kth term is removed from this list, that is, if you get rid of vk, then the span of the remaining list is still the same thing. So, in linearly dependent lists, this captures basically the idea I was saying before. There is extraneous information. That is, there are vectors that you can get rid of and still get the same thing using this tool called span. Let's prove this. Okay, so proof. Since v1 through vm is linearly dependent, which I'll write as lindep just to save myself a little bit of time, there are scalars, field elements, a1 up through am in the field, not all zero, such that a1 v1 plus dot 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 all the way up to am vm, that linear combination is equal to 0. Let's let k, I'll just say it in words, be the largest, largest, I'll just say largest number such that AK is non-zero. So basically, hey, not all of these guys are zero. There's at least one that's not zero. Let's pick the biggest one that is not zero. That is relative to this numbering. As we're from 1 up to m, there is at least one of them that's not zero. If there's more than one of them, let's pick the one whose number next to it is biggest. Okay, cool. Then notice, so if this says if this is the largest one that is non-zero, then a1 v1 plus dot 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 all the way up to ak vk plus ak plus 1 vk plus 1 plus dot 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 plus am vm, this whole thing right here, which notice we said is equal to 0, is then just equal to a1 v1 plus dot 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 ak vk. So this is the largest one that's not equal to 0, meaning that everything afterward is equal to 0. So the rest of these are plus zeros. Okay, fair enough. Cool. Now, here's what we'll do. Since it's non-zero, we can do a little bit of manipulation and see the following. Minus ak vk is equal to a1 v1 plus dot 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 all the way up to ak minus 1 vk minus 1. And since ak is not 0, we can multiply by its multiplicative inverse to get vk is equal to minus ak inverse a1 v1 plus dot 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 all the way up to minus ak inverse. That's a minus right there. Let me make that slightly clearer. Don't want that minus to get lost. ak inverse ak minus 1 vk minus 1. Hence, vk, as we have just explicitly shown, is in the span of v1 all the way up through vk minus 1. Oh, look, that's the first thing we wanted to show. So if v1 through vm is a linearly independent list in V, there is some k such that vk is in the span of v1 through vk minus 1. We just showed that. Nice. Furthermore, if k satisfies this condition above and the kth term is removed, then the span of the remaining list equals the span of the whole list. Now, to see this piece, notice the following. So, since, I'll say this, to see the rest, notice that this lets us rewrite any scaling of vk as a linear combo of v1 up through vk minus 1. That is, if you take the span of v1 through vm, notice you can get rid of any part that comes from vk and rewrite it in terms of v1 through vk minus 1. I can write this out, but it's going to be really tedious to do so. Just basically look at an element that looks like this, not equal to 0, but here, I don't want to write too long. Just, a linear combination, something like this. Doesn't have to be equal to 0. Any linear combination. Pick out the part that's next to vk, replace vk with this whole thing right here, group terms together, and hey, would you know it, everything is in terms of a linear combination of v1 through vm sans vk. Okay, cool. If you want to prove that yourself, just verify it. It is a very routine application of commutativity of addition and associativity, and also, I guess, distributivity of scalar multiplication over the vector space's addition. But cool, the linear dependence lemma. This will turn out to be a very big tool for us. And it basically says that anytime you have a linearly independent list, there is extraneous information in it relative to the subspace associated to that list. All right, let's do a little bit more. All right, here's the next result. So we're going to prove that the length of a linearly independent list is less than or equal to the length of a spanning list in any finite dimensional vector space. So take a finite dimensional vector space. What we're going to claim is that the length of every linearly independent list, every single one, is less than or equal to the length of every spanning list. So, proof. Here is the idea. All right, first off, let's let the span of, I'll call it W1 all the way up to Wn be V. i.e., suppose W1 all the way up through Wn is a spanning list. Okay, that is a list of vectors that spans V. That is, there's n of them. Suppose there's a list of length n that spans V. In particular, let's suppose that it's these things, W1 up through Wn. Okay. I'll say U1 up through UM be a linearly independent list. All right, what we want to show is that M is less than or equal to N. All right, so here's kind of the idea of it. What we want to do is we want to use the linear independence lemma, or the linear dependence lemma, to do a fancy trick. So, since W1 all the way up to Wn spans V, so does U1 W1 all the way up to Wn. Does everyone see why that is? That is, things that are in the span of W1 through Wn are just linear combinations of the W's. And so if you add an extra thing, just put 0 next to it in a linear combination, and you can still get all the linear combinations of the W's. So adding something to a list doesn't break its spanning property. Okay. So this is also a spanning list. Since U1 is in V, U1 W1 all the way up to Wn is linearly dependent. So, by the linear dependence lemma, I'll say there exists some k such that the list that you obtain by removing one of these guys is linearly, here's how I'll say it, such that U1, W1, up to WK spans V for some, I'll say some K less than or equal, or I'll say just strictly less than N. That is, we can get rid of one of these vectors, right? So at least one. So from U1 up to W1, we've now got a linearly dependent list. And so just going back to the linear dependence lemma, basically it says, hey, you can always remove something from your list and get a list that spans the same thing, right? So going up here, we can get rid of something. Here, let me be even carefuler. This is still a true statement, but what I want to do is I want to be extremely specific. So I will not do anything too fancy. Here, let me erase a piece of this and make this much more clear, because the way that we're using the linear dependence lemma is important. And I think if I don't highlight it, it might get lost. I'll even write it like this. So, let me, yep, there we go. Okay, so here's what I want to say. So by the linear dependence lemma, we now have a list of length n plus 1 that is linearly dependent. By the linear dependence lemma, I can get rid of at least one of the things from this list, right? Okay, so now I have a list that is length n. All right, cool. So here's what we're going to do. Now we'll do a bunch of steps. So this was step 1. Here is step k for k equal to 2 all the way up through m. Take your list from the previous step and notice that UK is in its span. So adding UK in the kth position in the list yields a linearly dependent list, and we can use the linear dependence lemma to remove an element. Since the start of this list is all ui's, and u1 through is linearly independent, we get that the removed element must be a w. I'll say a wi. Okay. Then, at the end of this, we get a list that looks like u1 all the way up through and then some w, I'll call it t, or I'll even write it like this, because I'll write it as t1, w, t2, and so on all the way up to w, t. I guess it should be n minus m, I believe. Yeah, because then there are n minus m w's right here and m u's, and so a total of n things right there, right? And if n is equal to m, then there are no w's right here, and we just have the u's. So maybe this is what this is. I should add a caveat where there are no w's in the case where n equals m. Okay, so in this case, hey, look, I've kind of gotten rid of a bunch of stuff. Every time I added a u, I got rid of one of the w's, right? Here I could get rid of some w. I could get rid of wk, right? All right, and now every time I did this, since I was just appending u's in the beginning, and the u's form a linearly independent list, the linear independence lemma lets us remove something, but we know it's not one of those u's since they can't be in the span of the previous elements in the list by linear independence. So it must have been one of the w's. Every time we can be removing a different w, so this is going to look like some messy bunch of indices. What I'm trying to say is there are just some w's left over. And now we get a list that looks like this that spans V. So the length of such a list must be at least as long as the length of the linearly independent list u1 through um, i.e. it has to be at least length m. That is what we wanted to show. We wanted to show that the length of every linearly independent list of vectors is less than or equal to the length of every spanning list of vectors. That is, the length of every spanning list can be at the very lowest the length of a linearly independent list. Nice. All right. Let's see if we can do some more. That's kind of a complicated proof. If you feel a little bit tripped up on it, feel free to send me an email. The idea is that we're just kind of doing an iterative process where we start out with our spanning list. We append at the very beginning something from our linearly independent list, right? We're going to put that right here. And then we remove something from the list using the linear dependence lemma. And we keep going like this until we've put the entire linearly independent list at the beginning. Cool. We still have a spanning list. And the best part is we've shown that this spanning list has to be at least as long as our linearly independent list. Nice. All right, let's keep going. Okay, last result of the day. Let's prove that every subspace of a finite dimensional vector space is also finite dimensional. This seems intuitive, but it is actually maybe not quite as easy to prove as you might first think. It's not a terrible proof, but it's going to rely on what we just did before, which was kind of involved. So here's the idea. Let V be a finite dimensional vector space. Then let's say let U be a subspace of V. Here's step one. If U is just the zero subspace, we are done since U is just equal to the span of the empty list. Okay. If not, let U1 in U be non-zero. Since if U is not equal to this, there must be something other than 0 in U. Okay, cool. Now, let's do the rest of it. Step, I'll say 2 through K, maybe? Here's the idea. So, we're going to proceed as if we were doing the second step. Okay. Take span of U1 all the way up to UK. In the second step, this would just be U1, right? I'll say even K minus, or I'll say J minus 1. here, I'll even make this more clear. Instead of saying step 2 through k, I'll say step j for j in 2 through some k. Okay, so we'll take the span of u1 through uj minus 1. In the case of step 2, this would just be the span of u1, right? If this is equal to u, we are done, since that means that u is finite dimensional. It's spanned by a finite list of vectors. All right. If not, take some uj in, or I'll say not in, how about, the span of u1 up through uj minus 1, and repeat now with span of u1 up through uj as the next step. Here is why this terminates. Now, since uj is not an element of the span of u1 up through uj minus 1, the list u1 up through uj is linearly independent. Kind of nice, right? By the previous result, the length of every linearly independent list in V is less than or equal to the length of any list that spans V. Okay, cool. Since V is finite dimensional, there is a finite length list that spans V. Oh, we've actually said that all lists are finite length, but just to really highlight that all lists are finite length, there's a finite list, a list that spans V. So there cannot be I'll say an arbitrary, so there, even better than there cannot be, let's say, so I'll say that, so there is an upper bound on how long a linearly independent list in V can be. This applies to the UIs. The process has to eventually stop at some k that is less than or equal to the length of any choice of a finite spanning list for V. Hence, we get that U is equal to the span of U1 up through UK, and U is finite dimensional. Done. Nice. Kind of a weird process, a little bit strange perhaps, but the gist of it is just that we start out with a finite dimensional, whoa, what's going on with my pen right here? Oop. We start out with a finite dimensional vector space, then we take an arbitrary subspace. Now, if that is the 0 subspace, we're done. If not, we'll grab a non-zero vector, and then we'll just keep doing this. We'll take the span of the previous vectors that we've used, and we'll see if this is equal to u. If it is, if it's equal to u, we are done, since now we've shown that u is spanned by a finite list of vectors, hence it is finite dimensional. If not, we'll take some uj that is not in the span of those guys, and we'll repeat this. However, since uj won't be in the span of u1 through uj minus 1, this tells us that the list u1 through uj is linearly independent. Since we know that every linearly independent list in V is less than or equal to the length of any list that spans V, the fact that V is spanned by a list of finitely many vectors means that this process can't go on forever. And so at some point, this is equal to u, and we are indeed done. That happens. So we are done at some point, and we get our result. Nice. That's pretty much everything for today. See you next time.